will be talking to you about colloids in a statistical sense. I'm actually going to mix together colloids, vortices, and a few other systems. But everything I talk about can be realized with colloids, so that's my justification here. So the first lecture will be on ratchets. And for those of you that are not familiar with ratchets, this is a system which is out of equilibrium by definition. And I'll first describe requirements. First, what is a ratchet effect and what are the requirements you need to have a ratchet, which is you have to break enough of the symmetries in the system, and again, you have to be out of equilibrium. Then I'll give a brief description of the soft matter simulations that we do in studying these systems. And then I'll give some examples, and I'm not sure that I'll actually cover all three of these. I'll probably cover two and briefly mention the third. The first ratchet example, which I'll give in the most detail, is a quasi-one-dimensional ratchet. It's sort of the closest thing to what you might imagine when you think of a ratchet. And in this system, since it's not really one-dimensional, it's actually two-dimensional, we can get a case where collective interactions will produce a ratchet reversal. So in other words, the ratchet will actually go the opposite direction than what you would have thought as you change a parameter in the system. The second example, which I may or may not cover, is a case of using colloids to do logic operations. So this would be, it's not going to replace your desktop computer, but you can actually do addition, subtraction, things like that with particle-based alternative logic architecture. But it turns out that in order to get this thing to work, you actually have to add a ratchet mechanism. So I'll show you the original proposal for it, why it didn't work, and why it would work if you used a ratchet. And the third example, which everyone always likes, is the bacteria ratchet. So this is kind of the limit of colloids that propel themselves. This was inspired by some experimental work done by Robert Austin's group at Princeton. And when Robert Austin presents it, he talks about it in terms of Maxwell's demon sorting bacteria from one side to the other. But by the time I get to this point of the talk, you should easily understand that this is actually just an extremely simple Brownian ratchet. And I have to say, if you really want to know everything about, well, a lot about ratchets, there's an excellent review by Pete Riemann in this reference. Okay, so first, what is a ratchet? The ratchet effect is defined as the emergence of directed transport in a spatially periodic system. So this is very simple. And the classic example of a ratchet is the Feynman-Slowakowski ratchet system, which you've probably already seen. So let me refresh you. The idea is that you have a circular disk which has got teeth that are asymmetric, so they're sharper on one side than on the other. And you have a little pawl that will it'll allow the disk to turn in this direction, but it's supposed to prevent the disk from turning in the opposite direction. And the way that this was originally proposed by Feynman, the idea was that if you had thermal fluctuations, you might be able to get the pawl to kind of thermally fluctuate off one of the teeth, and then the whole disk here would rotate by one tooth, and the pawl would re-engage. And so the idea is you could actually rectify thermal fluctuations. And so it seems like perpetuum mobile. The problem with this is, no, that doesn't actually work. And the reason is you don't break enough symmetry in the system. You've broken a spatial symmetry here, but you did not break time reversal symmetry. So if you're able to get the pawl to disengage from a tooth and allow the tooth to move forward, by exactly the same process, it can disengage from the tooth and the tooth can move backward. And the probability of those two things happening is exactly equal. So on average, this will not go anywhere, and you can't get free energy for nothing out of your thermal fluctuations. Question?
How come it's the equivalent is asymmetric?
Oh, so the asymmetry is spatial but non-temporal. So if you're able to, let's see, let me draw here's your asymmetric tooth, and here's your pawl engaged with the tooth. And the idea is that you have a thermal fluctuation that raises this pawl up above the tooth so that the tooth can move. And your naive expectation is that the tooth would move in the direction that would cause the ratcheting. But in fact, the tooth can move either direction. And so you're equally likely to run this ratchet forward as backward.
But if it's equally likely to go forward or backwards, it seems like there's more space on the side that goes forward, right?
No, it's the thing that stops it is when it's against this tooth. And so all that matters is, in other words, this part of the tooth is kind of irrelevant for this particular realization of a ratchet. It's always just when it hits this spot. So you can think of this as a bunch of discrete spots that the pawl is in contact with. And it's equally likely it'll go from this spot to this spot as from this spot to this spot. So you get no net rectification in this system. Okay, so let's talk more about symmetry and ratcheting. Excuse me. These are necessary but not sufficient conditions for a ratchet. You need to break symmetry. So one way is you can break spatial symmetry. Now you can do this.
Why did you put two thermal barriers on the previous slide?
Two thermal barriers. Okay, I grabbed this off the internet. People talk about how you can get this to actually work if you make it into a heat engine, essentially, and have this side coupled to one temperature and this side coupled to another temperature. The problem is you get thermal conduction along this rod, so it still doesn't work. People have tried to explain how you can get this to actually be a ratchet that will get energy out of thermal fluctuations. Okay, so you can break spatial symmetry, and the common way to do that is have a potential which is sharper on one side than on the other, but still periodic. It can also be, symmetry can be broken in a statistical sense. So it doesn't, this is sort of a deterministic symmetry breaking, but you could have random fluctuations that are colored. So they could either be Gaussian fluctuations or they could be non-Gaussian fluctuations. That's easier to see when you talk about breaking temporal symmetry. If you apply some kind of drive to your system, like you take this potential and you tip it back and forth, that breaks temporal symmetry because if your particle was moving to the right under your driving force, in the next instant of time, it's much more likely to continue to move to the right because your driving force is that way than it is to move to the left. So that breaks your temporal symmetry. And again, you can do that by applying a colored noise instead of a white noise to your system. So if you break enough of these symmetries, you can get a ratcheting effect. The Feynman ratchet only breaks spatial symmetry. It doesn't break temporal symmetry, so it doesn't actually work as a ratchet. In addition, the perturbations of the system have to be non-equilibrium to give you a ratchet effect. You cannot have a ratchet in an equilibrium system. Okay, so here are some ways that you can break symmetry. I drew one here. Spatial symmetry can be broken by having an asymmetric sawtooth potential, for example. You can also do other things, like you can have a spatially dependent friction coefficient. So suppose one area of your sample is kind of stickier than the other area. If you have that arranged asymmetrically in your system, that can break the spatial symmetry. And there's a lot of different ways that people break temporal symmetry. There are many types of ratchets, and I'm only going to talk to you about a few of them. A very famous one is the flashing potential. This is used in what are called stochastic ratchets. And the idea is here that you have a potential that the particle feels, and at some instant in time you turn that potential off, and the particle is able to move around under thermal fluctuations. And at another instant in time, you turn the potential back on. And after doing this over and over again, you can actually get the particle to transport across your system. The tilting potential is the one that you're kind of most familiar with. If you just drive your particles back and forth over your potential, or you can think of it as tipping your potential back and forth, that breaks the temporal symmetry also. This is a variation on the tilting potential. You could have an asymmetric AC drive. It has zero net mean force, but you spend different amount of time at each force. So suppose you spend a long time at a very low force in one direction, and a short time at a very large force in the opposite direction, so that the net the integral under the whole thing is zero. This can also give you a ratcheting effect. And then, of course, one case of breaking detailed balance, which I'll mention at the end, is if you have self-propelled particles. So if your little particle you're trying to ratchet actually has a motor, then that obviously doesn't obey detailed balance. So now let me give you some examples. There are questions on ratcheting. That was a really brief introduction. And now let me give you examples, and maybe you'll think of more questions as I go along.
Yeah, just before the previous slide, all these cases where you have temporal symmetry, it seems to me that all break detailed balance.
Yes, that's the point. You need to break detailed balance. That's right.
But then you could also replace temporal symmetry by breaking detailed balance, right?
Yes, that's right. Yes, that's right. I mean, it's kind of a semantic issue, how you want to call it. But the point is you need to break detailed balance, which makes these out of equilibrium. Okay, so the first example would be quasi-one-dimensional ratchet. And I'm going to show it to you in a superconducting vortex system, but you can do something extremely similar in a colloidal system. So the idea is we have a ratchet effect for vortices that are on a quasi one-dimensional asymmetric periodic substrate. If we have vortices that don't interact with each other, we get what you would call a normal ratchet effect. In other words, the vortices move in the direction you would have expected if you looked at the potential. But as we increase the vortex density and the vortices start interacting with each other more, we get a ratchet reversal. And this we can show is connected with local vortex structure. Now, in general, when you look at ratchets and you try to predict, if you can do analytic work with ratchets and decide which direction is the transport going to be, is it going to reverse? It turns out to be fairly difficult to predict reversals for these ratchets because it generally depends on higher order moments of the exact shape of the potential, which in effect is being changed by this vortex-vortex interaction. But I'll show you a bit more intuitively why we're getting the reversal that we see. So back in the 90s, there was a very simple proposal for a vortex ratchet. If you put superconducting vortices on a simple periodic asymmetric 1D substrate. And in the next slide, I'll introduce the superconducting vortex system. But here's the substrate that Lee Yanko and collaborators had in mind. You take a sample and you're able to fabricate a substrate that's basically an asymmetric sawtooth along the x direction, but on the y direction it's just constant. So this is why I call it quasi-one-dimensional. It's only modulated in one-dimensional, but there is a second degree of freedom for the objects here. So here you can see the shape of the potential, and you have a area where the force is going to push the vortices to the left, and an area where the force will push the vortices to the right. Okay, and let's introduce the system I'll be talking about, which is superconducting vortices. This is an example of a soft matter system. So you probably all know a superconductor has two main properties. It has perfect transport of current, making it the superconductor, but it also will completely expel a magnetic field. So this is the Meissner effect, and it's what distinguishes a superconductor from a perfect conductor. So here's the classic example of a superconductor in the Meissner state. Levitating over a strong magnet. There's a large class of superconductors known as type 2 superconductors, which includes all of these high temperature materials that were discovered about 20 years ago, which have the following properties. At low magnetic field and low enough temperature, the sample will be in the Meissner state. So here's a representation of the superconducting sample, and it's completely expelled the magnetic field. If you raise either temperature or field, you'll go back to the normal state. So at that point, you no longer have perfect transport of current, and now the magnetic field comes rushing back in, and it just penetrates the material like it would penetrate any normal material. But type 2 superconductors have a very large range of field and temperature, where they enter what's called a mixed state. And in this state, they essentially cheat. Rather than having the magnetic field completely come in and destroy all the superconductivity, they kind of make a compromise, and they say, well, magnetic field will be allowed to penetrate, but only in little quantized bundles, which are called vortices or flux quantas. And so at the center of each one of these is an equal amount of magnetic flux. Around the outside of each one is a circulating supercurrent, which screens the remaining material from the magnetic field. And so at the inside of this vortex, you have a spot of normal material, but outside the vortex, you still have superconducting material. So with this, the material is able to remain superconducting and move up to significantly higher fields and temperatures than it otherwise would. So these objects, these vortices, have quite interesting properties. You can think of them as magnetic field lines that have a physical realization. I mean, normally you kind of draw magnetic field lines, but they aren't really lines, they're a field. But in this case, you can think of this actually as a magnetic line with some line tension. These are all going to be directed in the same, all pointing in the same direction, so the vortices will repel each other. What happens is the circulating supercurrent from one vortex interacts with the magnetic field from another vortex, and it gives it a repulsive interaction. The vortex has a line energy due to the fact that superconductivity is suppressed at the core of the vortex. So the system would like to do whatever it can to try to reduce this line energy. So if you have any kind of defects in the material, you can get what's called pin. So this is what I like to call the theorist superconductor. It's completely perfect. The material absolutely superconducts everywhere. And if you have vortices in this case, you can think of them as just straight lines. When they repel each other, they'll form a triangular lattice. in 2 dimensions. This is the lowest energy lattice. It beats out the square lattice by about 2% in energy. And this is known as the Abrikosov vortex lattice. Alexei Abrikosov won the Nobel Prize for this discovery, which he made back in the 50s, I guess, just a few years ago. In his original paper, he got it a little wrong. He said they would be a square lattice, but they gave him the Nobel Prize anyway. So, as I said, this is the theorist's representation, but here's sort of closer to reality. When you make your superconducting sample, there's going to be some kind of inclusions in here that don't superconduct quite as well. Maybe it's an extra atom of the wrong phase, or a whole area of the wrong phase, or some book that got in there during the processing. But at any rate, at these spots, superconductivity is either suppressed or possibly even destroyed. What this means for the vortex is that since its core has an energy, which is related to how much the superconducting order parameter has to be suppressed, if the vortex can put its core on top of a spot where the superconducting order parameter is already suppressed, it can gain relative energy. So it would like to sit on these spots which are not as good superconductors. So what you wind up getting is, instead of this nice triangular lattice, you can have a situation where the vortices are all distorted out of place, and now they're sitting on these defects, which look like a rough landscape. And this general system has been used as a nice paradigm for having some kind of elastic lattice of interacting particles sitting on top of a rough landscape, because you can change how many particles, you can change the density of the particles, you can change the relative strength of their interaction just by adjusting the magnetic field. And then you can also change the importance of thermal fluctuations, which tends to reduce the interest of the vortex in sitting on this state of reduced superconductivity. At any rate, this turns out to be a good thing, actually, in terms of applications. And that's because if you want to use the superconductor to be a superconductor, you want to send a current through it. Now, a current, if it flows through here, it's going to interact with the vortices that are present. In fact, the current will actually generate some vortices of its own. And you'll have a current and a magnetic field, so that gives you a Lorentz force on the vortices. It's J cross B. So if I apply the current this way, the vortices are going to try to move this way. And for an application, you don't want the vortices to move. The reason is that at the center of each vortex, there's a normal core, so there's normal electrons. And if the vortex moves, it drags the normal electrons with it, and that dissipates energy. So you lose your true superconductivity. So it turns out that if you put gook into your material deliberately or accidentally, and it pins these vortices down, you can apply some finite current without having the vortices move. And so you maintain the true superconductivity even though vortices are present. The pinning can be altered by changing the sample. People do all kinds of lithography and other techniques to make artificial pinning these days. And the strength of the vortex interaction can be tuned by changing the magnetic field. And just to give you an idea of kind of the size scale of these things, this is an image of vortices in niobium. I believe this is a magneto-optic image, but I'm not positive about that. And the spacing between the vortices in this image is about 1 micron. The vortices are a little bit too small to see easily optically. They're a little smaller than the optical wavelength. Okay, so people have looked at superconducting systems to make ratchets. They made ratchets in a couple of ways. These are experimental examples. Here's an experiment where they artificially fabricated some pinning sites. So they went in and just drilled holes in their superconducting film. And they made one large hole next to one small hole. And what they saw is they did this and then put vortices on here and shook the vortices back and forth, they would get a net transport of vortices. So of course they've broken a spatial symmetry, broken temporal symmetry, they get a ratchet. What they found is that as they change the magnetic field over the temperature in which they're operating this system, the direction of the ratchet would change. So red here would be sort of a forward ratchet that you would expect. And then green would be switching to the backward ratchet. Red is a forward again. Green is a backward again. So they see a bunch of reversals as they're changing the magnetic field. And they basically observe this, but they don't really describe why these reversals are happening. Another group did a similar type of system where they made pinning sites that looked like this, triangles. And they just made a whole array of these triangles. And this winds up being very similar to, I'm not sure that the vortices even care that whether this is a triangle or not. So they get basically the same effect where they can get a forward ratchet, but actually if they shake the vortices back and forth not quite as hard, they got a backward ratchet. So once again, they're seeing ratchet reversals through the complicated interactions between vortices. Now we have actually studied this system, but I won't talk about it. Let me talk about one that's a little simpler, which is the 1D Yes, question.
So how is the time transition broken down?
How does it say again?
The time transition.
Oh, that's because we're shaking it back and forth with an AC field. So, as I said, that breaks detailed balance because at any instant, if you were already moving to the right, you're likely to continue already moving to the right rather than going to the left. You're not randomly going right and left.
So is this primarily to test Brownian ratchet theory rather than a specific application?
Well, so yeah, the two examples I showed you didn't really have a purpose other than to say, look, vortices can ratchet. There is actually an issue in some fields. People aren't aware of the literature that already exists on Brownian ratchet. So in particular, the bacteria ratchet, I'll tell you at the end, the experimentalists had no idea what the Brownian ratchet was, as far as I could tell. I mean, I talked to them. And so there's a certain amount of reinventing of the wheel that's happening, just because people aren't familiar with the ratchet literature. A lot's been done since the 90s in understanding these ratchets much better. However, the middle example, in principle, could have a real application of a ratchet effect. So I'll show you that one. Okay, so now let me talk to you a little bit about how we model this system. We take a phenomenological approach. We treat the vortices as just point-like objects which have some kind of pairwise interaction. This is coming from what's called the London approximation, and the idea is that, given the presence of a magnetic field from one vortex line and the supercurrent around it, and the presence of the magnetic field from another vortex line, we just find the interaction between those two vortices. And we will perform particle-based simulation of these vortices, and we use what are called Brownian dynamics or overdamped dynamics. The reason being that, as far as anyone can tell, there's no evidence that vortices have mass. So essentially what this means is that the vortex is moving through an extremely viscous medium, which is, of course, just the superelectrons and other electrons in the system. As long as there's a force acting on the vortex, it will move. But as soon as that force is removed, it immediately stops. It doesn't keep going for a while, no inertia at all. So that means instead of F equals ma, we have F equals eta times v. So in our case, eta, we're just going to take the v1. It's related to the normal state resistivity of the material. The velocity of our particle is going to be proportional to the interaction force between individual vortices, which we treat pairwise. Thermal forces is from the dynamics. Interaction with our substrate, whatever that might be, and then interaction with the driving force. So let me go through these terms one at a time. The vortex-vortex interaction force, we're going to treat the vortices as if they're perfectly stiff lines. And for low-temperature materials, this probably isn't a bad approximation. So the idea is that even though there is a z component of the extent of the vortex, we're going to pretend it doesn't matter and that the vortex is just stiff. Yes, question?
So I understand in low temperature that's a really good approximation, but as you're in these mixed phases, isn't how much of that can be treated as a single line without any distortion related to the size of the sample, the thickness of the sample?
Yeah, so the key is in the low temperature materials, thermal fluctuations are so small that the vortex really does stay pretty stiff. I mean, it's got fairly large line tension. But in the high temperature materials like info and especially visco, that's no longer true. I mean, you're often running these things at liquid nitrogen temperature, and their thermal fluctuations are definitely significant. So this model becomes not very good, and especially for something like visco, where you can actually break this apart into what are called pancake vortices on each line. We could maybe say we're representing one slice, but not really the whole sample. We have done modeling of the 3D system, which I could talk to you about separately. But there's some other issues if you try to do that, because now you have Josephson vortices going through as well. Those are very difficult to study. But in those cases, an alternative would be something like the Ginsburg-Landau or XY type of approach, which people do. So this is really staying simple and just looking at the 2D interactions of a lattice with disorder. Okay, so as I said, we're treating this as a stiff line, and that means we're also averaging the thinning along the length of the line, which makes a lot of sense in these artificially engineered thinning systems. The vortex-vortex interaction force is simply given by the Bessel function. So those of you that are plotting through Jackson already have plotted through Jackson. Yes, Bessel functions really do show up in real world. So of course it's a cylindrical Bessel function because we have two cylindrical objects interacting with each other. Happens to be K1 in particular. So this function falls off exponentially as R increases, which is very nice because it lets us truncate the potential without having to do an Euler sum or something like that in our system. The other terms here, we're doing essentially Brownian dynamics to these vortices. So we have a thermal force that arises from random longitude kicks. Generally, what I'm going to show you is going to be actually at 0 temperature. But we can turn temperature on, so the average, each particle receives a kick at each time step, which is drawn from a Gaussian that has a mean of 0 and a standard deviation that's proportional to the temperature according to the fluctuation of space there. Question?
Is it important that you have a bezel function interaction, or with a simple screen exponential interaction?
Oh, how much does it matter? Well, it doesn't really, it only matters quantitatively, I would say, because what we've seen already is that if we take a vortex system, which we're representing with the Bessel function, and we take a colloid system, which we often represent with the screen Coulomb, we get the same qualitative behavior for each one. It's just energy scales will shift a little bit. So it seems that it's not that particular about the exact choice of potential, the sorts of things that we study. Even long-range potentials, there are a few changes, like if we do a Coulomb rather than screen Coulomb, we still get similar behaviors, a little bit more different. Big difference comes if we go to a granular potential, which I'll discuss in the third talk, because then since particles have no idea that they're going to interact and float on top of each other, that really changes the way that they behave. Question?
You have thermal noise with the fluctuation dissipation theorem on the slide. Is there a microscopic reason we should expect that to be true and not some other?
Well, so in the superconductor, you could argue, and this was actually, this Brownian dynamics technique was developed in the 70s with the idea of modeling something like a colloid being bashed by the microscopic water particles. In the case of the vortex, it's most likely going to be phonons wandering around in the material, something like that, that will cause these thermal fluctuations. And again, for the low TC materials, they aren't very significant. It's mostly in the high TC materials that you worry about temperature.
Sorry, the vortex inversion force. Can you just simply draw how?
How put that on this slide.
Yeah.
So the K1, it's basically, if I can draw it, this falls off as an exponential.
Yeah. Okay.
And then the divergence, I believe, goes like 1 over the square root of r. We don't take this, so if the vortices get too close together, we do truncate it. But in our case, they never get that close together. So there is a limit. In other words, we can't go right up to HC2 where the cores start to overlap. This model technically was developed for 0.2 HC2 and below, but people have pushed it quite a bit above that and it seems to work. In the same way that people have, Ginsburg-Landau is supposed to work only very close to HC2 and people have pushed it way below HC2.
What's the reason that the vortex interaction is not the same as between two wires?
Because there's supercurrent. I mean, there's superconductor in between them, so it's not air. Yeah. In fact, this is a different interaction than if they were fluid vortices, which will tend to rotate around each other. So that's not the same as these. I had somebody that did fluids on my thesis committee. That was his question. Okay, the other forces, we have a Lorentz driving force, which is coming from an external applied current. So as I said, this is just J cross C. And then the pinning force, so this is going to be our substrate potential. And we represent this very simply. Often we just represent defects as little parabolic traps. Well, on the next slide, I'll show you how we're representing the asymmetric potential that we're using in this system. Okay, so here's our potential. And this is just showing a slice of it. In the y direction, it's simply constant along y. But in the x direction, we have modulation with an asymmetric maximum. So if you look, this is the shape of the potential. Here's actually the force that the vortex experiences. If it's in this part of space, it has a positive force, and if it's in this part of space, it has a negative force. And so you take this system, you have an easy direction of motion, which is this way, and the hard direction of motion, which is this way. And we're just going to apply an AC drive, which is a square wave with equal duty cycles. And again, this, even though this doesn't look asymmetric, this does break time symmetry. So that's the two symmetries that we break. This will have a magnitude of FD, so that's how tall this is, and a period of T, which will vary just how long we spend on one duty cycle. Okay, so what we get is if you just depin the vortices, don't shake them back and forth, but just push them, what you find is that the depinning force is different for the two directions. So if you push them in the forward direction, that's the easy flow direction, then they'll be pinned, they'll be stuck basically because they can't get over that barrier without thermal fluctuations, and at some point they'll be pinned and then flow freely in that direction. And if we go in the opposite direction, then it's harder to get them to move, and then they will eventually move. So you can see that in this regime, we've got the ability to move in one direction but not in the other. So if we set the amplitude of our AC drive somewhere here, you would naively expect, well, they're just going to go forward because they've already been pinned in the forward direction and we haven't been pinned in the backwards. Whereas if we raise our force to here, they should still go forward but at a reduced rate. So this is what we actually get as a function of driving force and the period of our drive. This is how much ratcheting we find. And this is always in the positive direction. So here's a lot. They move forward quite rapidly. And then as you go down into the blue, they move forward less and less rapidly. So we have a lot of structure here. Let's take a look at where it originates. So there's a threshold here. If for a given period our driving force is not large enough, nothing moves. And of course this is easy to understand because you have to be able to get all the way from one side of the tooth to the other in order to be able to ratchet. If the driving force is too low or the period is too short, you'll just stay on one tooth the whole time, so obviously you can't ratchet. And you can actually write down, well, therefore, this line should go roughly like 1 over the driving force, and that's exactly what we see. We take it cut this way, at fixed driving force. What you see is that as a function of our period, we get some structure in how much ratcheting we get. So we get these peaks at these values of the period. And it turns out that's simply a matching effect of when we're able to travel exactly one period of the ratchet or 2 periods of the ratchet or 3. And so once again, you can simply write down an expression for where these peaks should appear, and it falls exactly where we'd expect. So far, our ratchet's behaving nicely, like we think it should be. Question?
What about temperature?
Yeah, so far this is 0 temperature. And actually, I will not apply temperature to this system. Is that true? Yeah. So the temperature, of course, makes things more interesting. It tends to smear out the ratchet effect, first of all, so you get less ratcheting. But since I'll show you that we do have a ratchet reversal, there's a general theorem that if you have a reversal as a function of one parameter, you should get a reversal as a function of any other parameter. So you should actually be able to reverse the ratchet with temperature as well. We didn't study that, but in principle it should happen. So what happens as we start increasing the vortex density? Here are the vortices as they sit in our potential. And of course, they'd like to sit at the minimum of the potential. This is when there's no drive applied to them. But eventually, if we put too many vortices in here, they do have a second degree of freedom available, so they'll start buckling out of the minimum because they don't want to cram. They no longer want to sit so close to each other that the potential's not that deep, so they start to go out into the y direction. And eventually, they'll start making multiple rows. You can actually study interactions here. Well, what does this mean for the ratcheting? As we start changing the density of the vortices here, so we're increasing the number of vortices in our system from something like 300 up to 2,000, we actually get a reversal in the depinning forces. So before forward had a low depinning force and reverse had a high depinning force, we actually get a case where the reverse depinning force drops dramatically and drops below the forward depinning force. So of course, this is a ratchet reversal. So this is just showing the fact that the pinning force in the 2 directions as a function of how many vortices we have will cross each other. And so this is kind of the origin of the reversal that we get. So here's actually seeing the reversal. Here's the velocity as a function either of the number of vortices. So here we start out with a positive velocity, and we reverse to negative velocity over a wide range of edge. And it looks like we're just barely getting back to a positive velocity again, but this is 6,000 vortices. This is quite a lot. Question?
Yeah, that function looks rather complicated. Is there,
yes.
In terms of n, do you have any idea about?
In analytics? No. So even for relatively simple potentials where you're just looking at one particle going through, to find where the reversal happens is very sensitively dependent on higher order moments of the function. And in general, people can't write that down analytically. But it's just, you know that it reverses, but you can't predict where. And so it's even worse here because now we have this whole lattice structure. We can, however, so like I said, we're getting a reversal as a function of the number of vortices, and then also if we fix the frequency and change our driving force, if the driving force is small, we'll get a reverse ratchet, but as we increase the drive, we'll actually get a positive ratchet, depending if we have enough vortices, not for a low number of vortices. So you can kind of see, let's see, and here's our equivalent of the experimental plot I showed you before, where we have a positive ratchet effect as a function of driving amplitude and number of vortices, then a negative ratchet effect, and then another the tip of another positive ratchet effect out here. So let's take a look at what the vortices are doing as we drive them forward and backward. And this gives you kind of an idea of where it's not analytic, but it's sort of qualitative of where the reversal is coming from. When we drive the vortices in the positive direction, which normally would be the direction you expect the ratchet to go, you can see that they kind of spread out and do their best to form a triangular lattice. So they're minimizing their interaction potential. But when we push them against the hard direction of the ratchet, the way they aren't supposed to go, they wind up lining up along the potential. And that brings the vortices closer together, and it actually helps them to overcome the potential better. The vortex-vortex interaction force is stronger here than it is here. And so that actually helps them go over the potential more easily in this case than in this case. So that's how we get the switching from this being the easier decaying to this actually being the easier decaying at higher end. And what happens at very high end, which we barely got to, is when you get up around 6,000 vortices, you start to get a triangular lattice again, even in this case. It's basically just triangular all the time. It doesn't care about the potential. So then you go back to this being the easy direction again. And presumably, there would be more reversals even higher, but we can't get there with that simulation. Okay, so that was my first question.
Yes. I was wondering that if you tried to realize this in a colloidal system, you would have probably charged species of colloids, and then you would have ionic species floating around as it creates the screen coolant effect. If you applied a AC electric force, then you would have the colloids wanting to move in one direction, but you would have a counterflow of ions. And I wonder if qualitatively you can ever properly take that into account.
So this is essentially electrophoretic forces are, that's a complicating fact with the colloidal systems. And it's something that colloidal people complain about in their models. You can worry about also hydrodynamic interactions because you've also got the water flowing around. Often with if you're in the electrophoretic regime, you can get counterflow of the ions that'll sort of cancel out the hydrodynamics essentially. So there's some hope that in that regime you might be able to still see these effects. It would have to be tried, but yes, it's definitely a complication. Whereas if you try to sediment them, I think the hydrodynamics would probably kill you. They would dominate, and then you would see something different. So, but yeah, it's an issue when you look at these systems. Okay, so question?
Yeah, maybe I understood wrong, but did you say temperature is 0?
For what I just showed you, that was all zero temperature. So thermal fluctuations didn't play a role in this ratchet.
Okay, but then how far is it actually a ratchet? I mean, fluctuations don't play a role.
Oh, but it's not in equilibrium. I mean, it's sort of completely out of equilibrium. Because, like I said, we've broken time reversal symmetry with our AC drive, and we broke spatial symmetry with our spatial potential. So that gives us the ratchet. If we just let the vortices sit there, they won't go anywhere. I mean, so that. Or if we just put thermal fluctuations on but no drive, we won't get a ratchet. So they won't thermally move to the right. We didn't try that, but that should be true, which is why we didn't try it.
And is there a theorem that proves that?
Theorem.
Great.
Well, let's see. I refer you to the Riemann review for if there's a theorem. I mean, he discusses it at considerable length. I'm not sure if he makes it mathematically rigorous.
I think Riemann just says that if there's any symmetry saying that it can't happen, then it
Yeah.
won't.
Let's see. There's a name for that.
Curry's principle.
Yes, Curry's principle, which basically says if it can't happen, it will happen, essentially. If there's no symmetry that forbids it from happening, it'll happen. So yeah, you read the review here. Ask him. It's an excellent review.
Just a note, it's Reimann, it's not Riemann.
Oh, I'm sorry.
Yeah, it's Reimann.
Well, that's okay. I'm Reichhardt, but not Reichhardt. So. Okay, let's see. Well, let me briefly tell you about the colloidal logic and then get on to the bacteria, which everybody always likes. So this is sort of also an introduction. Since I'm supposed to be talking about colloids, I should actually talk about colloids a little bit. As you may know, colloids are simply an inclusion of one phase in another phase. That's the definition of a colloid. So what we're typically working with is a solid phase and a liquid phase. And these are particles which are density matched normally, so that they'll just sit forever, well, in principle, never stay forever in physics, in the sample without sedimenting at all. And so typically physicists work with polystyrene sulfate spheres, which are sort of in the micron range of size. This is convenient because that way you can point a video camera at it and see what the particles are doing. They can be in 2D or 3D. We're going to focus on systems where the colloids have been confined to 2 dimensions by some means, either by letting them sediment to the bottom or confining them with lasers. We're going to look just at monodisperse colloids, and we'll consider the case where they're charged. And there's all kinds of real-world applications for colloids. Ink is a very important one. If you had a glass of milk this morning, there's lots of colloids in food frames. You can manipulate colloids with a laser beam, and so you can make what's called an optical trap. You shine a laser beam into your colloidal system such that you focus it at a spot, and then you have a dielectric colloid interacting with that laser beam. What will happen is that, suppose this is the most intense spot of the laser, laser light will be diffracted through the colloid, and if the colloid isn't right at the center of the laser spot, there's going to be momentum transfer where more laser light is diffracted this way than that way, and that winds up giving a net force on the colloid this way, towards the minimum. So if it can sit in the minimum, it'll have equal amount of momentum transfer and it'll actually be trapped right there. So by turning up or down the strength of your laser, you can increase the strength of this potential. And people can look at either just individual potentials, or they can make whole arrays of these, do interferometry. There's quite a bit that's been done. Our computational modeling of the colloids looks almost identical to our computational modeling of the vortices, except now we have a screen-coulomb interaction. So here what we're saying is that we just have pairwise interactions again, once again over again. Of course, this really is Brownian dynamics now. And the colloid-colloid interaction we take to be screen-coulomb, so the idea is that there's a surface charge on the colloids, which usually occurs when you place them in water. And then around that there's some ions inside your fluid which do the screening. Not too many ions, or we completely screen. We do neglect hydrodynamic interactions in this model. And then we'll have the colloids interact with the substrate. So let me tell you about the ratchet effect that we tried for the colloids in the context of logic. And first of all, what is this logic? Well, the idea was to make an alternative logic device using the discrete positions of particles in some kind of traps. So this was proposed by Lent et al. Back in the early 90s. And they thought, well, let's take 4 quantum dots and have 2 electrons in them. And if we do that, the electrons are going to sit either like this or like this to minimize their energy. So we can claim, well, this is the logic state 0, and this is the logic state 1. And now we can use these little quantum dots to make a logic device. So if we have, here's our pairs of quantum dots, we arrange them like this. If we flip these dots, it's going to send a signal through, and all of these will interact, and this can be set up to be either an AND or an OR gate. But basically, the idea is you just propagate a signal. If you flip one of these, then the rest of them are going to start flipping kind of like dominoes. That's the idea. Sounded good. So we thought, well, you could do that for colloids. We could just take elongated traps, and I can show you. You can actually make something like this with 3 lasers to make 3 spots, and the colloid will think it's 1 spot. So suppose we had a line of these traps, and we have the colloids. They're either going to sit up, down, up, down, up, down, or they're going to sit down, up, down, up, down, up. So we can propagate a signal by just flipping from up to down. So the place where they flip is going to be actually the signal. And so we thought, well, this sounds good. We can simulate this, and we'll just take this thing and flip this particle from here to there, and we'll watch our signal go right on down through the line. We thought, great, done. Right? We set up the simulation, and it completely failed. It didn't go anywhere at all. We flipped this dot, and this dot had no idea anything happened. Why didn't it work? Well, there's a problem with the system, which is state indeterminacy. You naively think that it will work because you're used to working with massive systems. If you shake a rope, inertia is going to carry what you've done with the shaking through the rope. But these are overdamped systems, so there's no inertia. There's nothing that will carry the particle over the well once it's going. So if we take this state and we flip this particle from here to there, this middle particle will start moving, but when it gets here, it's perfectly happy. Right? It'll just stop and say, okay, I'm halfway between these 2 particles. There's no reason for it to continue going up here. In fact, it doesn't want to do that because it's going to get closer to this part. So it just stops, and that's the end of our logic transmission. Now, we tried adding temperature, because we thought, well, let's thermally kick it, and it'll have some chance of going that way, and then we can get the signal to propagate. And we were able to get signals to propagate purely diffusively. So they were just as equally likely to go to the right as to the left. And so you couldn't, you could wait at the end of your chain for a signal, but chances are good you'll have to be waiting for a really long time before it gets there.
Excuse me, so these tracks then, if I look at them as a potential, they're flat bottom?
Well, that's how we were representing them here. The actual colloidal ones look more like this. So that there's kind of two. This was to try to discourage them from sitting in the middle.
Yeah,
but it turns out to be not enough. So yeah, we did try this. But then actually that kind of makes it worse because it doesn't even want to go to the middle in the first place, and it'll just kind of hang out right below the middle, and not even go over the top. So this alone, we tried it. This alone doesn't do it. So we found a solution though, which is to actually apply a ratchet to this system. So here's kind of an example where a ratchet can be used to do something useful. What we do is we change our pin. So we make 3 species of pins instead of only 1. The first pin still looks like our original pins, but the other 2 we make them wider, and we bias them so that the particle would like to sit either to the left or to the right of each one. And then we add to this an AC drive which has a 3-state cycle. So the first state is off. The second state is to the right, so we push everybody to the right side of the potential. Well, let's see, sorry. The first state is to the left, so we push everybody to the left side of the potential. And the third state is to the right, so we push everybody to the right side of the system. And what we've done is we've actually made a ratchet because we've broken spatial symmetry and we've broken temporal symmetry. How does this help us? So let's take a look. What we're doing is we're altering the spacing between the particles so that we have a near spacing where we want the particles to interact so that they'll flip. And we have a far spacing so that the particles won't prevent each other from flipping. So in this case, this is the off state of the 3-state drive. These 2 particles are close together. We've just flipped this one. So this one is coupled to this one, but weakly coupled to that one. So it'll go ahead and flip all the way up to the top of our potential. Then it'll stop because these are far apart. So now we apply the leftward drive, which is just enough to move this guy from this side of the potential to this side, but not to kick him all the way out. And now these 2 particles are close together, but these 2 are far apart. And so now these will be coupled and they'll go to the bottom, and this won't prevent it from going to the bottom. And the next slide I have up for the next stage here. So the next stage is now we push everybody to the right, and now these 2 are coupled. These 2 are decoupled because they're far apart. Now this guy will be able to flip, and now we've made it through one complete stage. And so what you see is that we're actually just propagating the spacing. Here's A, the short spacing, and A prime, the long spacing, simply walking it through the array. And so what we can do is we can get our signal to follow this spacing through the array. So now we have deterministic transport of our signal. And if we have this type of potential and no thermal fluctuations and the 3-state drive that I showed you, we can get transport of our signal, but it's a little lossy. So sometimes it skips a tooth. But by adding the right amount of temperature, not too much, you can actually get the system into a regime where it will propagate completely deterministically. So obviously, if you wanted to do logic operations, this is what you want to do. Okay, now you can, by playing with the spacing, you can start making gates with this, but let me not go into that detail. And there was a colloidal realization of this. Rather than making different shapes of wells, Clemens Vestinger's group was able to make sets of wells that they simply slide back and forth because they have a device. I can't use this analogy anymore. It's like an old-fashioned television where it will raster the laser beam through the system and make spots where you want it to make spots. So they can move the spots on a time scale. Well, it rasters it so fast that the colloids don't realize there's kind of only one laser. And then they can move these gates around. So they move the traps around. They move them such that they replicate the effect that we had with our shaped wells and a 3-stage drive. And they actually get exactly the effect that we predicted. They're able to get a signal to propagate from one side of a Fanout gate, in this case, to the other. And unfortunately, I used to be able to play this movie on a computer, but I cannot get this to play. So if you go to Clemens Vestinger's website, you can watch this little movie and see the signal propagate. So it's pretty slow. It's less than a hertz. So you're not going to be using this to reproduce, to change what you're doing on your laptop or anything. But it does show you that you can do this propagation. It's actually relevant to transport of signals in biological systems, because this is, it may be that if you try to get a signal from one side to another in a cell, you may actually need to use a ratchet mechanism to get it to go only forward and not backward, because in that case, thermal fluctuations are so strong. Okay. All right, so now the final example, which everybody usually likes, is bacteria. And the bacteria ratchet is a case of self-driven particles. So, of course, the particles themselves break time over to symmetry. And our work on this ratchet was inspired by work that you saw in Robert Austin's group. So if you have a chance to see him give a talk, it's very entertaining. He did a very nice talk on their work. And he just, the way he sets it up, he describes their system as seemingly having a Maxwell's Demon effect. I think that was the title he used his talk, Maxwell's Demon Bacteria. And however, now since this is a lecture course, as I show you this system, look for the broken symmetries that don't make this Maxwell's Demon. They actually make it a realization of a simple Brownian ratchet. And see how quickly you can understand why this is working. So let me give you a little bit of the flavor of how Bob Austin sets this up. First he talks about, of course, the second law of thermodynamics. I'm sure you've already heard about this or know about it. And the idea is, of course, your entropy has to increase with time. It can't ever decrease. And so if you have all the gas molecules in one corner of the room, they're going to spread out and cover the whole room because there's more states, and they're never going to go from here to there. Well, in principle they could, but the likelihood that they're all going to suddenly cluster in the corner and we'll all die is so small that I wouldn't lose any sleep over it. Now, of course, Maxwell's Demon is a case where Maxwell proposed that you could have a system which has got mixed species of A and B with a little door in between. And if you have a demon that watches the door, it'll open the door whenever a red particle is coming and approaching to the right, or a blue particle is coming and approaching to the left, and otherwise it'll close the door. And so over time, you can wind up with a system that was mixed and winds up being separate, which is, of course, a lower entropy state. You would expect the normal progression to be from here to there. So it seems like, oh, the second law of thermodynamics was violated. Of course, the issue here is that this is not a thermodynamic object. The demon is non-thermodynamic. And so, yes, you can violate the second law if you're not in thermodynamic equilibrium, so no problem. All right, so now let's take a look at symmetry, which, as you know, is very important in these ratcheting processes. So imagine if you had a room with this geometry. We have a room with a divider, and we have two doors, and we open the doors like this. Now, you do not expect that because you have broken symmetry of the room, all the air molecules from this side are going to go over to the air molecule to this side, and everybody on this side of the room will suffocate. If we've got a door open back there at an angle, we'd be in trouble. So obviously, you sort of know that this won't happen. If it did happen, you would claim, well, there must be some kind of demon present that's causing the air to violate thermodynamics here. Well, what happens if you don't do this with air, but you do it with bacteria? This is what Bob Austin did. And he doesn't exactly motivate very clearly why they decided to do this, but it's quite a nice experiment now that they've done it. They made a nanopropagated array of these little barriers, and you can see that they're asymmetric. So let me zoom in so you can see there's actually a hole in between each of these hosts, so the bacteria will be able to go through. And you might look at this and say, well, it should be easier for the bacteria to go this way than that way, in principle. Except, if this is sort of like the air analogy. You would think, well, I mean, that's the argument I made for the air all going to one side of the room, but it doesn't happen. What happens if it's bacteria? Well, what they did is they put fluorescing E. coli into the system and started it out with uniform density, and then over time, they waited, and this is something like 30 minutes, I believe. They saw that the bacteria all concentrated on one side of the container. In fact, here's the ratio of the density of bacteria on this side to that side. You can see as a function of time, it just goes up and then sort of saturates. So somehow, the bacteria are all rushing to one side of the room, and that doesn't seem to make sense. They looked at a few things that control this. First of all, they said, well, you have to have a funnel. Here they reverse the direction of their funnel. If you have the funnel shape, you get the rectification, but if you get the concentration. But if you just make flat barriers or barriers that are not asymmetric, then the bacteria all stay uniformly concentrated. And they also looked at what happens if the bacteria don't swim. So they, I believe they genetically modified the bacteria so that they didn't have flagella. They just sort of, floated around. like a Brownian particle, either that or if the bacteria die, then the same thing happens. But what they see is that these red ones are the ones that can't swim, and they're just uniformly spaced, and they've got an array of these asymmetric posts here. But the ones that can swim, boy, they all rush over to the end. So his claim was, this is how you separate the living from the dead. So this is the concentration of the ones that can't swim, and this is the concentration of the ones that can. Okay, so now you ask, well, all right, so why are they rectifying? Now, hopefully, after the rest of my talk, it's already obvious to you why this happens. But it was not obvious to the experimentalists because they didn't read the review that was mentioned earlier. Ryman? Ryman. All right, so you can ask a bunch of things. Of course, the bacteria swim asymmetrically. They have a motor force. You can ask, well, does the motor placement matter? Does the fact that these E. coli are actually rod-shaped, does that have something to do with it? If we had circular bacteria, did we do it? Could it be chemotaxis, like somehow the bacteria smell chemically something that they like up on the other side? Or even some kind of hydrodynamic interactions? There are lots of different suggestions. So we decided, well, let's do something really simple and set up a very simple model for the single bacteria. The way that these E. coli move is that they will run in a straight line for a certain distance, actually a certain amount of time, and then they'll tumble, so they'll mix their flagella all up, and then they'll run off in a new direction. And I believe the amount of time they spend running kind of depends on how much food they have, and tries to help them stay in an area where food is concentrated. But essentially, what you say is that on long times, the bacteria acts like a Brownian particle, and you have to go to the Brownian limit. Because on very long time, you don't care how long it's spent running and tumbling. But on short times, it acts ballistically. So on a short enough time scale, it does break the cell bounce. If it was already going to the right, there was a high probability that it would keep going to the right and not go to the left. And so we say, well, that's all you need to explain the phenomena that Bob Austin is seeing. And so the demon is actually the fact that this is really a Brownian ratchet. So here was our simple model. It should look familiar to you now. Overdamped particles, which have, in our case, we're going to turn off the interaction between particles. We just have non-interacting particles. They swim. So we just have the particles move in a fixed direction for a certain amount of time. They change their mind and move in a new random direction. And we'll set how long that time is that they swim. We turn on, well, let's see. Yeah, well, we turn on the thermal force, what I'll show you. And then they interact with these barriers. And the way that they interact with the barriers, is if they're swimming they're trying to swim, say, this direction, what they'll do is when they hit a barrier, the component of motion perpendicular to the barrier is just taken away, and they'll continue to try to move this way, but only with the component of motion that's along the barrier. So they'll swim along the barrier, but slower. That's the way we've chosen to represent the barriers. Well, it's consistent with what they see. Now, it's not actually necessary to get the effect. Other types of interactions with the wall will work, except this one won't. If they come to the wall and bounce off it. So if you reflect their velocity when they hit the wall, that won't work. But it's very unlikely that that's what they do. So they might, the other thing they could do is they can train with the wall, and then they would swim with their full velocity along the wall. And that'll actually still give you the same thing as the way that we've modeled it, except I think they'll separate a little bit faster. Okay, so what happens is we let the bacteria swim around, and we take some length over which they swim, and it's fairly long. It's longer than the length scale of these barriers, and that's important. So initially we start with them all uniform, and then over time, what we see is they tend to concentrate at the top. Not only that, they do tend to pile up along the walls and they form kind of a plaque. And they do actually see that in the experiment. They don't really talk about it, but let's see. You can kind of see there's an increased density, there's an increased fluorescence right along the wall. So they do tend to kind of mush up against the walls. If we look at the density of the bacteria in our system, the ratio on one side of the barriers to the other, we see that it increases with time, and then it saturates. And the level to which this ratio saturates is a function of how long we let the bacteria swim before we make them turn. So if we let them swim for a really long time before they turn, then we get a fairly high separation. And then if we don't let them swim quite as long, the amount of separation decreases until finally, if they turn at every single time step, we don't get any separation at all. But,
what if you make your ballistic climb exponentially?
We didn't try that. Yeah,
will be.
you'd get less overall rectification.
Whether you'll get the
What you-
average or whether you'll.
Yeah, I guess it would
essentially
depend
be
how we did it. If we said this bacteria will always have an LB of 1 and this one will have 50 and we distribute it like that, you're going to wind up with the ones with short LBs uniform and the ones with long LBs sorted. Whereas if you do it every time they switch,
Exactly.
then I think you'll still get the separation. It'll just be slow. It'll take longer.
Interesting, or whether that.
Yeah, we didn't
mimics,
try that, yeah.
Surrounding particles.
Whether it'll go back. I think it'll just slow this. I think you'll still get the separation because what you're really doing, what you're really doing. I mean, you can think of this as just shaking the bacteria up and down. It's only that component of their motion that matters, and that alone will separate them. So anything that gives them this motion with a large enough amplitude will separate the bacteria.
If you run it, let me know.
Okay, you got a student to send me? Question?
Yeah. So when you said that the important thing is that the distance they travel during the run has to be long compared to the asymmetry of the barrier.
Yeah.
Oppositely.
Let me show next slide. Perfectly good. So what's really happening?
About the LB. What are the dimensions compared to the barrier? I mean, if you can go back to the previous one. This LB, what is the length of the barrier?
Oh, so the barrier on this scale is 5. Yeah, you mentioned that. So these are actually, you really only get no rectification for quite short LB. And the reason is that if you look at this, here's some LB. What's happening is that as long as this is long enough, you're going to run along the barrier for some significant amount of time on the path, and that's what's going to give you that. You're going to experience the asymmetry of the potential, and that will give you the rectification. Whereas if your LB is short, or if you're just a grounding particle, you contact the wall, but the very next instant you probably step away from the wall. So the fact that this wall is here doesn't even matter. You just are randomly diffusing around, so you don't realize that you're in an asymmetric situation. Whereas here, you're able to sample it and see it.
So it's easier to concentrate reindeer than the rabbits.
Yes. Unless I guess you'd have to have really small tracks for the rabbits. Questions?
So it seems that the reason there's a separation is because of the refraction of the wall.
Yeah, well, that's the asymmetry. I mean, that's the spatial asymmetry. So like I said, you need two things. This is the spatial asymmetry, which you have to have. This is the temporal asymmetry, which you also have to have. The temporal is the fact that if it was already going this direction, it's probably going to keep going that direction. So I have, over some period of time, a broken detailed balance.
And for molecules?
Oh, well, for molecules, they're going to act more like this. At any instant, they're going to go in some new random direction. I mean, there's no reason that a gas molecule is going to keep going to the right. It'll just be buffeted around by the other molecules. That's why all the air in the room doesn't rush to the other side.
No, it's very rarefied.
Well, okay, I guess if you tried this experiment in a very evacuated room, you could probably get rectification. So
If the mean free path is long
compared to the size of your asymmetric barrier, But in normal situations, that's not true with gases.
But, I mean, wouldn't the collisions with the wall be nearly elastic?
Well, that's true. So you would bounce off the wall.
Yeah, you showed that doesn't work.
And that doesn't work. Yeah. So you have to interact with the wall. So the motor of the bacteria keeps it running along the wall even once it's contacted the wall, whereas a molecule will just bounce off, and that doesn't work. Okay. Is there?
So if you have momentum conservation.
Oh, these are overdamped. Yeah, if you have momentum, that will change what's happening.
The bouncing off would.
That'd be more likely, I would say. Yeah. So that would probably stop it from working.
So the fact that this is done at low Reynolds number is very important.
Yes, exactly. That's right. Yes. I didn't mention Reynolds number here, but this is all life at low Reynolds number for bacteria. So let me just show you a movie of the two cases. Here's your thermally interacting bacteria. You can see they really don't care that there are barriers. Whereas here are our ballistic bacteria. You can watch them run along the sides of these potentials and get caught under these and everything. So this is just zoomed in on a small part of the sample. So here we get the rectification where they'll eventually wind up mostly up here or concentrated up here. And here we don't get anything. The concentration just remains constant. Question?
What's the time scale for how long it takes to separate?
Let's see, did I have a plot of that? It's related to the LV. Okay. Go back here. Yeah, I don't think I would call that, but it's related to where we are on this LV, how quickly you saturate. Basically, if LV is larger, you saturate faster. And by setting, I didn't put this slide, but if we choose LV such that it's sort of the right physical length scale for bacteria compared to the size of our barrier, and then convert everything else to physical units, we get a separation time which is very similar to what they see in the experiment. So it seems like they probably have their bacteria non-interacting with it as well.
So on the left panel, you just get diffusion, right?
Yeah, this is just diffusions. These are just thermally, and basically we put LV to one time step. Question?
Did you ever come across a situation where you got to that sort of layer?
Oh, reversal. We did not see that. We didn't look for it. It's not clear. Well, okay, if we turn on interactions, it might be possible. So we did a little bit with, we turned on some steric interactions so that the bacteria can't sit right at the same spot. And what you start getting is they'll start clogging up the opening. So if too many of them try to go through, it'll slow them down. All we saw is that it reduced the ratchet, but we didn't take it far enough to potentially get a reversal. There's no guarantee, like I said, it's extremely difficult to predict whether there's a reversal or not, so there's no guarantee that this system shows a reversal. But if it does show it for one parameter, it should show it for other parameters. So we could also maybe change the spacing of these barriers and see it. We did a little of that, we didn't see evidence of a reversal, so this might not have one. Which I think we're kind of going into the discussion section, right? And that's the end. So more questions? And
Okay. Thank you very much. More questions, please? Yeah.
So you can imagine, so I know that folks are very interested in this idea of quorum sensing. And I'm wondering if you have considered putting in a quorum sensing interaction in this type of ratchet so that the concentration gets too large. There's some signal to the bacteria that, hey, they need to spread out.
Yeah, we hadn't thought about that. I mean, one thing
would you predict that would reverse the ratchet?
Well, like I said, it's so hard to predict that. Well, one thing, so we haven't tried any, this is really all we've done with the bacteria, but I know that Bob Austin has the system set up where he put a food gradient in opposite to the ratchet, so that the bacteria will swim, they'll try to swim to the top, but all the food's down at the bottom. And what his idea was, he wanted to see if they would evolve so that they would swim against the ratchet so that they could eat. And I didn't hear, I think he's running it now, whether he made like super bacteria. So there's all kinds, that's kind of a combination of a chemotax and it's just, it's different.
I guess in that sort of experiment, I would expect that the directed evolution would lead to shorter crumble times.
Exactly.
Or shorter run
it
times.
would try to make you look brownie so that you wouldn't go through the ratchet. And then if you put the bacteria in a ratchet again, and you put the food on the other side, you can, I guess this is what people are doing with bacteria these days, but I'm glad I'm not a bacteria.
So what are the interesting theoretical problems? It seems like there's still fun experimental projects.
In other words, what's not known about ratchets already? So the hard problems in ratchets are things, like I said, predicting the reversals. It's not understood how to do that in a general way, because it turns out to be very difficult analytically to treat that, except I think there's very, very special cases where we can solve it. So that's one open question. But actually, a huge amount has been learned about ratchets in the past 20 years. And so, like I said, a lot of fields are kind of rediscovering the ratchet and not even realizing that that's what they have. And so more people should learn about what we already know about ratchets. This talk actually was on an area that we understand well. My next talk will be an area that we're sort of barely understand, and the last talk is going to be something we don't know anything about. So I'm starting off easy.
Okay, you got questions? Yeah, please.
So you said that as the diffuser motion increases and the ballistic motion decreases, you lose rectification.
That's right.
But it might just be that the rectification occurs at a much larger time scale.
Yeah, well, that's true. Yeah, that's true. So eventually, so then it becomes an issue of time scale. We just didn't run the simulation long enough to wait to see the tiny amount. It's not only that there's less rectification, but it saturates at a lower level. And so it becomes hard to detect whether you actually got separation or not. So I think I had how much, this is how much, this is the ratio, and this was, of course, after a fixed amount of time. But how much they went to the top compared to being on down to the bottom. And you can see that that drops off really quickly as I get to short LV. So not only would you have to wait a long time, but you're going to be looking at a small signal. And we hit issues with discreteness of our systems. Can't really measure it that well.
Okay, can you go back to your colloid logic gate?
Which part of it?
The one where you have the actual logic gate. So,
probably this one? Or?
Yeah. So my question is, what is the relative ratio of the time scale between the actual switching that you can do between individual colloids and the time it takes the signal to propagate?
So this is a question of speed. How fast can it? So you have to wait. Your duty cycle of your 3-stage drive cannot exceed the time it takes for the particle to go from one side to the other. Otherwise, you're going to start getting slipping events. In fact, if you, let's see. Yeah, you'll get something that starts to look like this. If you go too fast, your signal won't necessarily keep up with your spacing that you're propagating through the array, and you'll sometimes miss. And so you'll get more and more slipping, and eventually it'll just be all slips, and you'll lose your signal.
Yeah, so I mean, that sort of signal, like the top signal sort of looks like minus and stepping on a...
Well, yeah, so that's actually an interesting point, which is, as I said, this method of transporting something could be something that biological systems could use. What you're really doing, and what got the experimentalists interested in this, Clemens was trying to find a way to couple some stochastic resonators so that he could get a signal to move through a series of stochastic resonators. But he had exactly the same problem which we did, which is that the system would just diffuse, and you couldn't get it to propagate. But by adding the ratchet, then you could actually get it to propagate. And I did put these results in here. We did look at this. As you start playing with temperature now, you can kind of spontaneously get a signal and get it to propagate. And you can have new kinks appear. What you're doing is you're making a kink and a kink. And what we saw is if you get that, then actually both the kink and the anti-kink will go forward. And so these are the kinds of things you think, well, maybe a biological system would harness this. If it set up something that's kind of like this ratchet, and even though it's slipping, that's good enough for a biological system. Maybe the myosin kind of grabs on and works its way through the cell. So that's the very interesting biological connection with this work.
Yeah.
Sorry, when you're talking about the increasing the vortex density for the first example, there was some structure to the plot for the deepening transition in against the hard edge. And I was just trying to sort of understand.
Oh, you mean here?
Go back one slide. Yeah. So it seems like there's. It seems like it's almost.
You mean here?
Yeah.
So structure. So you mean that this is moving around?
I'm talking about it seems like it's discontinuous. Like it becomes discontinuous at a certain.
Oh, you mean the sharpness of it?
Yeah, the sharpness. Yeah.
Well, so let's see. These have not been renormalized to the number of particles in our system, so the overall magnitude of the signal is just going up. So it's going to look sharper, even though it's not actually sharper. So what you should look at is this that's been divided by the number of particles in the system.
Okay. Any further questions? Not that saying thank you again. We reconvene in half an hour.